So we'll get started for today and continue our discussion with Perceptron, rather conclude and move on to the next topic. So recap the problem setting that given m data points, we were trying to associate class labels with them. Now the class labels we considered in the simple case, which in some sense is also a canonical case, is the two class setting. You have points labeled plus 1 and minus 1. And if they were separable linearly, we developed a simple algorithm, the Perceptron classifier. But in general, we argued that even if the separating surface was complex between the two classes, we could have a cascade of classifiers. That's something we'll develop upon. So you could have also had points like this, not completely linearly separable, but for example, you could develop piecewise linear separators. Let's erase these. You could have separators such as these. However, to begin with, we decided to try and conclude algorithmic and convergence related issues with a simple classifier, which is the Perceptron classifier. And we discussed several applications, but then one application kind of kept appearing as a motivation, and that was spam detection. And I had motivated spam detection to explain concepts such as, spam could be of multiple types, and that's why there could be there's a motivation for going through several intermediate steps of classification. Anyways, there are other applications such as digit recognition, medical diagnosis, whether a person has a particular disease or not, classifying biodiversity, buying and selling products, and so on. Whether a person will buy or sell, whether a person will buy, for example, is what recommender systems are interested in. So Amazon would often recommend certain products to you because you have had a history of purchasing related products in the past, right? So these are all classification problems. In the latter case, buying and selling products, Amazon wants to classify whether this person will buy or not. So the simplest of the classifiers, Perceptron, tries to overcome a limitation of a naive regression based classification. So we identified that linear regression, say with constraint y is plus 1 minus 1, has some limitations because a plus 5 and a plus 7, right, both these predictions should actually be collapsed into a single label plus 1, which unfortunately regression doesn't understand. So whereas Perceptron tries to be explicit, so linear regression with this constraint does not acknowledge that plus 5 is closer to say plus 1 than say minus 1 is to plus 1, right. So minus 1 and plus 1 are actually very far away as far as classification is concerned, whereas 5 and 1 should be close enough. And Perceptron, on the other hand, it says, well, all of these are going to have the same label, so the only rule is for y equals minus 1, W transpose phi x should be less than 0 for y equals plus 1, W transpose phi x should be greater than or equal to 0. And we collapse these two into just saying for all x comma y pairs you would require, at least in the training data, y times W transpose phi x greater than 0 is a sufficient condition. Okay, I hope you see the clear difference between linear regression and the requirement that perceptron begins, and which is going to be the requirement with several other classifiers. Yeah. So question is, how do we deal with the zero problem? It's generally desirable that points don't lie on the classifier. So we'll kind of persist with the sufficient condition for most classification. The other possibility is to break ties arbitrarily. Now it also turns out that if at all there was a classifier with points lying on the surface, we could also shift it a bit and actually get strict separation with some epsilon. So strict separation is what we'll target. And this was a perceptron update rule. We motivated this perceptron update rule using this misclassification condition. What is the misclassification condition? W transpose phi x for at the kth iterate should kind of be on the wrong side, which is y times W transpose phi x should be less than 0. So this W transpose phi x is called the signed distance. And if you multiply it by y, you expect it to be unsigned, and that's called the unsigned distance. And we have trouble when the unsigned distance is signed, right? Okay, supposedly unsigned quantity is signed, and we saw that post this update we actually get a better unsigned distance. So moment you let's say I identify this point which is misclassified, this distance which should have been unsigned is actually coming out to be signed because it's on the wrong side. This is negative unsigned distance y times W transpose phi x, but after update it has come to the right side, and this would mean a positive unsigned distance. The same one, I mean this is wk plus 1 updated weight dot product with phi x. Okay, so this is the motivation behind the perceptron update. Now it may not become positive in one shot. So for example, this again has negative, this plus positive point also has negative unsigned distance. Its distance has got corrected, but that may not always be the case, right? So this was the intuition. We left off at this point. So we saw that the unsigned distance after update is going to be greater than the unsigned distance before update. okay, and it's greater, and it therefore the possibility of it being positive is just higher. More hope that this point is correctly classified now, but this is just an intuition. So now we will try and understand why it's guaranteed to converge if the points are linearly separable. Okay, so can you give me some idea how you would prove that this perceptron update algorithm is going to converge in finite number of iterations, obviously, and you can make use of the assumption that there exists a W for which the separation is achieved. Okay, so we'll assume that for all W such that for all xy in train, y times W transpose x. So I'll be using x instead of phi x just to make our life easier. So we'll assume that this is actually greater than 0. Now, there exists a W for which this is greater than 0. So if you want to call this W star. Okay, so assuming this happens, we want to prove that the perceptron update rule will converge in a finite number of iterations. So I want you to now suggest how you would go about with such a proof. What are the elements? The algorithm is written on the slide. What you want to get to is written on the board. Now you can prompt how you would go about this. I want you to think. The convergence criterion is here, written here. Repeat until the sign matches for all points. Now this is the same as saying that y into W transpose phi x is greater than 0, or rather is strictly greater than 0 is also fine, because by sign we mean the sign of the non-zero quantity. Okay, so you are suggesting that the accumulated weight should look like this. And then what will you do with this? Let us say this plus some W0 initial weight. Pardon? There has to be a learning rate as well. So you're going back to the previous observation that increase in the value of y wk plus 1 transpose phi x over the previous one, right? The signed unsigned distance. Increase in unsigned distance is at least eta times absolute norm of phi square. Right. You put neta here. Now how will you use this across all training examples? See, this certainly tells you that you have to assume something about 5x square. Okay, I'm going to write it as x square, just to, let's just keep it as x prime. Okay. Now how does this help? But this is for a specific example. Okay. So certainly norm x square is of interest. So let's actually write down quantities that are of interest. We'll see how to put together the story. Any other quantity of interest here? Is this of interest? Y times W transpose X across, for each training point. Okay, so now let's take a few steps back. I mean, we are given this. We know that points are linearly separable. This is supposed to be the unsigned distance, y w transpose x, right? It's the unsigned distance. And just to be consistent with what I'll write later, I'll write it as y x transpose. It's the same thing. I know this should be strictly positive. Can I now consider the minimum value it takes across all the points? So if it's strictly positive, then it takes some strictly positive minimum value across all the trading data points, right? So I will consider that, and that basically will correspond to what? It is the smallest, the shortest, the closest point, right? The distance of the closest point from the margin, from the separating surface, that's called the margin. Okay, so specifically, unsigned distance of point closest to W star is called the margin. So there is some margin that I can assume exists in the W star, in the case of W star. No, unsigned distance is with respect to W star. Let me put W star. Is that clear? So these are things. Now, what about norm x square? I mean, can I assume that there is one big ball that encompasses all the points? Ultimately, the points are given to me, right? So can I assume that there is this sphere? Okay, the sphere of radius norm x, of radius what? Max over x norm x. Containing all points. Can I also assume that? Okay. So I can assume that this is less than or equal to some r. Can I, so that's one way to do it. The other way to do it is instead of scaling, instead of normalizing x, I could also normalize w. I can say that, see, we are looking at dot product, right? I can say that norm w is equal to 1, right? So either you can scale the x space or the w space. So I claim that I can do this. So either I can do norm some radius, norm x less than radius, or I can also assume that norm w star is 1. Okay, I mean a little bit of leap of faith, but I hope you are able to see the connection. Ultimately, scaling up x and scaling up w, you can compact x while pushing on the scale factor into w, or vice versa. Okay, so now let's why is this called a perceptron? Because this is inspiration drawn from neurons. Features are input, each feature associated with the weight, and the activation is quantified by the sum of weighted features. So the activation is basically summation over wi xi, right? That's the activation. And by scaling norm w star to 1, we mean upscaling xi's, right? So by downscaling norm w star to 1, you are basically upscaling the xi's. So you can either increase the activation or the weight associated, the impulse or the weight associated with the impulse. You can basically adjust one against the other. Okay. So since perceptron can model linearly separable functions, I'll just recap the claims we are making. One, if there exists w star, that is points are linearly separable. And w star is such that y x transpose w star is greater than 0 for all x comma y in the data set. Then without loss of generality, understand WLOG, right? Without loss of generality, we can assume norm w star is 1. That's the first point, and that y x transpose w is greater than some margin. That's basically the summary of what we have written the board, and now we are going to build on it. So I'll give the margin some name. Okay. So as I said in the convergence discussion, we are going to refer to phi x simply as x. So again, just stating the same thing here. Okay, so I have made use of this, that points are within one. Just a second. So I made use of the other. So let me write the both conditions. So either way is fine. Let me write both the conditions. No, but then the w will scale correspondingly, right? W star will scale correspondingly. Yes. So we are making a transformation to the data and letting the w also take a transformation, so that you have the equivalent set of conditions required for separability. But it's simply a scale transformation. It's not a rotational or, okay, so it's a scale transformation. Yeah, I mean this is, so your question is just let's scale all the x's. So if you want to maintain the same margin, right, if you want this quantity to be the same, then you have to scale, if you scale x down, you have to scale w star up, w up. Yeah, that's what I'm saying. So then you have to scale margin as well. You can do all that. I mean, so you can scale two things: decrease the margin, right? Basically, shrink all the points, make the W also shrink, and then also shrink the margin. I'm trying to just play around with X and W and keep the margin unaffected. So we'll let the margin be unaffected and deal with either scaling X to within a sphere or making the W norm constrained. Okay, so let's assume that the data is scaled to lie in a Euclidean ball of radius 1, and let's also assume that U is unit length vector, which means that we have actually scaled the margin. Okay, so Anuj made this point that you could scale down the margin. That's what we have done. We have said that U is unit length vector, data is scaled to lie in the Euclidean ball of radius 1, norm x is less than equal to 1. Okay, this U is basically W star. So what have we done? We have said norm x is less than equal to 1, norm W, which I now call U, is 1, and these two lead to rescaling margin. Okay, you can visualize all that in this example. Just bringing points closer together, but you're not in this process of scaling, you're not affecting linear separability, right? Now you can, as I said, the tutorial I'll bring up this problem in slightly different way. You can kind of convince yourself that all these are not going to affect convergence, proof of convergence. Is this clear? So we are assuming these two, and we have still a margin. Yeah. So we have been I mentioned this in last class. This question is, should the unsigned distance be just this, y times w transpose x, or should it also be normalized by the length of w? So I said that all this is modulo w, right? So ultimately I mean, having fixed the space, we are just comparing two different values. So the absolute value actually is not very important to us. We are only interested in relative values. Is this clear? So now we want to take this convergence proof ahead. How would you do that? What quantities would you look for now? So what is a perceptron update step doing? At every step consists of you want to show that this can go to U, right, or this can go to some scaled version of U. Directionally this W and your Wk for very large values of k is compatible with U. Okay, so we also define this margin of separation, and we want to show that for large values of k the margin will always be positive, rather the unsigned distance will become positive, and this margin is with respect to the U that actually separates the points. So I've given it a name here, eta. Say gamma, this is gamma. Let me change this W star to U. Okay. So here's the result we want to prove, that if there exists a unit vector u such that yw transpose x is greater than or equal to gamma for all x, then the number of weight updates made by the perceptron update algorithm is at most 1 upon gamma square, where this gamma is what is going to influence the number of iterations. Okay, so we are saying that 1 upon the square of this margin is the lower bound, sorry, is the upper bound for the number of update steps. So this separator wk is going to move around for at most 1 upon the square of this separator, the separating distance. So this is the claim we are making. And at most t equals 1 upon gamma square iterations, we will have this condition satisfied for all points, the condition that unsigned distance is greater than 0. This is assuming that the unsigned distance of points closest to the targeted u is gamma, and all the points are lying within a sphere of radius 1. The target u, which is we are interested in the direction and not really the magnitude, so the magnitude is also 1. Okay, so to do this, as I have already hinted, we are going to track two quantities. We are going to track w transpose u, okay, so we are going to look at a dot product, but instead of a dot product with respect to x, we are looking at a dot product of w that is being updated at every step with the targeted u. Okay, so we are interested in a dot product, but why this dot product will become clear in a few iterations, in a few slides. And the other one we are looking at is norm w square. Okay, so earlier I had said that norm x square was of interest to us, but we already compressed the x to lie within a sphere of radius 1. Okay, so in some sense now we put the onus on w, the norm of w. So the norm of w, you would like it basically to shrink, right? You may start with some arbitrary w. No, I have yet not put a constraint on where I start w's from, but I am going to inspect how norm w square behaves and how w transpose u behaves. Okay, yes, here, okay, yeah, so basically I think I have assumed eta to be 1, so let me just simplify it. We assume eta to be 1. Okay, so let us write down what this update rule means. So when you do w plus x transpose u, which is the dot product after update, so as you can see on the board, this is greater than or equal to w transpose u plus the margin, right? This x transpose u is upper bounded by gamma. y is plus minus 1, so the upper bound will still hold. So this is the first finding. Can you give me a similar finding for norm w square? That should be simple. So norm w square before and after update. So this is after update is relation with what happens before update. Okay, so norm w square, instead of that I look at norm of w plus x square. So similarly help me complete this. What is norm w plus x square? So I have given you hint from this slide, on this slide, and I want you to complete the next slide. What will be the relation between norm w square after update and norm w square before update? And I can make use of this, the fact that all x's lie within the sphere of radius 1 centered at 0, the origin. So can you expand this? This is w transpose w. So can the TS move around? I want to make sure everyone gets this. Oh sorry, x. Okay, I want you to complete the story. So we have 2 steps. What do you do with all of this? So on the slide we have shown that w after update, its dot product with u will be greater than w, its dot product with u before the update, plus some margin. The margin is exactly gamma, the distance of the point closest to the separating surface with respect to the true separator, a true separator. There could be multiple true separators, there could be multiple separators. This is one separator u. So that was the first equation or inequality. The second inequality is that the norm of w after the update is less than equal to the norm of w before the update, plus some dot product, 2 times dot product term between w and x, and 1, which is the radius of the circle which contains all the points. Okay, now how do you leverage these two? The second of the inequalities is proved here. So there's an interesting additional step here, additional observation we make here. What is that? What do I know about w transpose x? Oh, I didn't add the y, I'm sorry. Yeah, how do you get this? I think I've here also I've missed the y. Oh yeah, okay, so did I say that? For a positive example, okay. Fine. But let's write on the board in general for any y. Okay, so what do you know about W transpose X for a positive example, or in general for any XY that was used to update W? What do I know about W transpose Y times W transpose X? I do this update only if the unsigned distance is signed, which is negative. Right? So I have additionally made use of this fact that W transpose XY will be negative if that was used in the first place. So I can actually get rid of that in the right hand side, or if you want you can do the following: W transpose Y W transpose X plus norm X square, which is 1 less than 1, which is further less than norm W square plus 1. Okay, so I have written it as an additional step. So we have two observations. One is norm W square for positive and negative examples increases by at most 1, and this dot product with U, the target U, increases by at least gamma. So assuming the following we have got so far: now if you want you can put an call this WK plus 1, call this WK, right? So how do you make use of these observations to prove this 1 upon gamma square as an upper bound? Where do you think 1 upon gamma, where does gamma square come? Here is gamma. Okay, so I'll get going with the proof and keep prompting for inputs. So let's say we keep doing this update for k steps. In the slides we have assumed that y is 1, but in the board we are trying to consider both y plus 1 and minus 1. Okay, so when you put together these two inequalities, you keep doing this for k updates, right? Then you will get this update after k steps will be at least greater than or equal to k gamma. Let's say for the time being, you initialize with w equals 0 weights, right? And again this will be less than k. So if w0 is 0, right, and if you were to think of this as WK. Let me use U transpose WK. So if W0 is 0, then after K steps you will have WK is greater than equal to K gamma, and norm WK square is less than K. Okay, so this is the same as saying that non WK is greater than equal to, less than equal to root K, and yeah, the same inequality. U transpose WK is greater than equal to K gamma, and we have, as someone pointed out, which is a well known inequality that we can use here. Cauchy-Schwarz. So what is the Cauchy-Schwarz inequality? X transpose Y is less than equal to 2 norm X into 2 norm Y, and when does equality hold? X and Y are parallel, right? Or X is the same direction as Y. So what do we know about the norm of U? It is 1. So by that, since 2 norm of U is 1, we will have that WK transpose or U transpose WK is less than equal to norm of WK. Now does this help you? K is greater than equal to, so where is gamma square going to come? Okay, so you know that root K is greater than equal to K gamma, which means that K is less than equal to root K is greater than equal to K gamma, which implies that K is less than equal to 1 upon gamma square. So was that similar to your line of reasoning? 0. 0 resulting from, right. Right. So this is one line of proof. This is not the only line of proof. Okay, and this line of proof makes some assumptions to get you two things. One is convergence, and at the same time the order. I mean, how fast it converges. But you are completely right. If you change your initialization, will you have a different rate of convergence? So in the tutorial, I will try and pose this question slightly differently. So if you go on the web and try looking for proof of convergence or perceptron update, you will find multiple variants. So tutorial, I will try to give you another flavor in the next tutorial. I probably have it in the tutorial already, is it? Tutorial 3 I think already has another version of this. Okay, so this is the idea. Just putting together inequalities, you get K is less than equal to 1 by gamma square. And as I pointed out, this is one version of proof that assumes W0 is 0 gives rate of convergence and also proof of convergence. Now does this anywhere depend directly on the features? How good or bad the features were that were designed? Pardon? As long as there is a solution, right? So the convergence doesn't depend on the features as long as there is a solution, but the rate does depend on the margin, right? The margin that exists here. So that might be influenced by the features. See, to get to this margin gamma, we've kind of rescaled the data. So the data rescaling of W has affected the margin gamma. So that should be kept in mind. So you can arrive at what conclusion? That the features will affect. So his point is, we can infer that features influence the rate of convergence only if this is the strongest bound. Is that necessary? Why are you insisting on a strongest bound? The gamma is a lower bound on the margin. Yeah, but my point is, our assumptions have all been stated. So if you can get a stronger bound, but does the convergence get affected by change of features? No, not as long as they are still separable, right? So I already agree that the rate of convergence could be influenced by feature, for example, feature rescaling. Why? Because the entire process we have rescaled the margin by shrinking all the points to lie within a sphere. So that we already done. So that's already acknowledged. But the convergence itself will not depend as long as the points are linearly separable. Right. So what exactly is a perceptron update rule optimizing? What is this step optimizing? So we are looking at if y w transpose x is less than 0, then do this update, right? So we write down if y w transpose x is less than 0, then you update. Eta has been left out, any settings. Okay, so but let's just complete it, else W remains as it is. Okay, so one way of viewing this is that there is a loss only when there is the unsigned distance becoming negative. So the unsigned distance is kind of determining the loss. So let's try and plot this. So we are saying that if this unsigned distance is negative, then there is a loss, and there is some loss, else the loss is 0. The loss view in terms of the unsigned distance, y w transpose x. Is that correct? Implicitly that's what is happening. So this is like a step loss. There is a loss. Now whether the loss is, whether the loss has some gradient or not is another question, but certainly it suddenly vanishes at 0, right? So let's try and consider this loss function. So it says let's try and plot this. So I've used minus of y fwx where fwx is the perceptron classifier, is W transpose X. So it says that if minus of Y W transpose X, if this turns out to be 0, if this turns out to be negative, then the loss is 0, else it's exactly this term. Okay, so on the y axis you have this hinge loss LP FWX comma y, and on the x axis you have minus of y FWX. Okay, so the loss becomes non-zero only when minus y FWX is non-negative, right? So there is this kink here. It is continuous but not differentiable. Okay. So what exactly perceptron does is apply something called gradient descent, but a variant of gradient descent, stochastic gradient descent, on this loss function, the loss function given by LP. So consider an example which is misclassified, amounts to saying that for all the correctly classified points the loss is 0. So in some sense you can say, well, I don't even care for whether the point is correctly classified or not. So just consider a set of examples xi, yid, choose any example xt, yt, because the loss will determine whether xt, yt should be taken seriously or not. And now you are going to just do gradient descent, but you are doing gradient for that example only. So here compute the gradient of the loss, this is loss on that example. So this gradient update based on loss computed on a single example is called stochastic gradient. It's a version of stochastic update. You are not considering all examples, one example, that too drawn randomly, sampled randomly, and this particular loss for which stochastic gradient descent is applied, which results in perceptron, is called the hinge loss. Okay. So summarily what we are saying is perceptron update is stochastic gradient descent on hinge loss. So now you can just convince yourself that this is indeed the case. You can just compute the gradient. I mean the gradient of y times fwx, if that turns out to be the max component, is nothing but, it's just x, right, gradient with respect to w, and it's minus x, but since you are doing descent, so you can just verify this quickly. Let's just write this down. The gradient with respect to w of LP fwx comma y is nothing but minus of y times x if minus y x transpose w is greater than 0, or the signed loss is less than 0. So in those cases this will be w plus yx, negative of the negative quantity minus yx. That's exactly perceptron update. Okay. So somebody had asked, a couple of you had asked this question, is perceptron update applies pretty heuristic, but there is some optimization motivation behind the perceptron update algorithm. Is that clear? So this is what we observe here. Step 2 of the stochastic gradient descent gives exactly this, the perceptron update. Any questions? Yes, so you could do that, you could have multiple updates, just that with the hinge loss, because there is this kink at 0, it's possible that your classifier changes even after a single update. And the examples we showed, so the question was why not do bulk update, why single update? Is because the classifier does change with every example update. And there are also other reasons. There are some nice asymptotic properties of stochastic algorithms. If you are interested, you can talk to me offline. It's also very easy to implement. So now what weight vector should we use for evaluation finally? So use the final W at test time, that's not always a good idea, because you have gone through stochastic updates. What you often do is something called voted perceptron. You count the votes for weight vectors, how many times, how many examples they correctly classified, right. So you could have gone through multiple iterations, and let us say W5, it had could have a vote of 20 examples, and as against that W100 could have a vote of 21 examples. Maybe for all the iterations that you did, just one additional example got correctly classified, because it's after all a best effort. So voted perceptron says, well, let's give weightage to those intermediate W's and take a weighted average. That's voted perceptron. So don't take all of don't take only the final one, but this is a heuristic after all. There is also average perceptron, which says, well, give equal importance to all the weight vectors that you get. Yeah. So question is this to prevent overfitting from happening? Yes. Right. So it's possible that the classifier that I have got has just managed to classify all the points, whereas some points were really noise, you shouldn't be trying to classify them. So that behavior generalizes well on test data. Average perceptron is just where you give equal weightage to all the intermediate W's. Now it's not that you have to use all the intermediate W's, you could use some of the intermediate W's. Obviously you don't want to use W0 where you began, right? You'll say, well, I'll use W50 and 100. So W5 is a bit too much to start off with. Let's say W95, that might be still meaningful. Okay. So we'll continue with the next topic, building on perceptron, in the next class.